Hello, this is question 3 from the 2015 MAT. So in this question we shall investigate when functions are close approximations to each other. So we define modulus x to be equal to x if x is greater than or equal to 0 and to minus x if x is less than 0. So yeah, we're just knocking off the minus sign if there is one. With this notation we say that a function f is an excellent approximation to a function g if the magnitude of the difference between them is less than 1 over 320 whenever x is between 0 and a half inclusive, and it's a good approximation if it's less than or equal to 1 over 100, right, in the same range. For example, any function f is an excellent approximation to itself. Well, it would be if x is an excellent approximation to g, then f is certainly a good approximation, yeah, because that's a less strict condition, but the converse need not hold. Well, it doesn't, certainly indeed. Part 1, give an example of two functions f and g such that f is a good approximation to g, but f is not an excellent approximation to g. Right, there's going to be an infinite number of things we can write down for that. So we want the difference between them to be somewhere less than or equal to 1 over 100, but not as small as 1 over 320. So say we had f of x was, well, we're going to want to subtract them. So let's have something in common. We'll have those x's that will cancel out. And then if we just have that being 1 over 100, well, you could have any number between, in fact, you don't even need x in it. You could just leave the x out. But any number between 1 over 100 and 1 over 320 will do. So when we subtract g of x from f of x, I mean, we could even have the 1 over 100 down here on g of x because we're taking the modulus. But yeah, we subtract those and we get 1 over 100, which satisfies good but not excellent, which is what we wanted. Okay, so yeah, you've probably got a different answer to me on that one, but it all comes out the same. Show that if f of x equals that and g of x equals that, then f is an excellent approximation. So excellent. So we want to be in this top one. So we're going to do f of x minus g of x. So f of x minus g of x is going to be equal to, well, the x's cancel. So we got minus sine 4 squared over 400. And well, we're taking the modulus of that. So if we put a modulus around this, then the most we're going to get on the right hand side is what, 1 on the top. So that's going to be less than or equal to 1 over 400, which then, well, that's less than 1 over 320. So therefore, excellent approximation. Okay, right, there's plenty more of this, as you'd expect, on the next slide. For the remainder of the question, we are going to try and find a good approximation to the exponential function. Okay, this function we should call h satisfies this equation. I'm just going to write down the numbers. It was 1 over 320 when it 1 over 100. So that was excellent and good. That's on the previous slide. So that is our h. This is our approximation to the exponential function. Right, you may not use any other properties of the exponential function during this question. Okay, any attempt to do so will receive no marks. Right, so let f of x equal that. Show that if g of x is this, then f is an excellent approximation to g. So g of x, oh, we've got an integral of f of x there. So, well, f of t, but same thing. So g of x is going to be equal to 1 plus, then we want to integrate this thing. So we'll get t plus t squared over 2 plus t cubed over 6 plus t to the 4 over 24 between 0 and x. So we're just going to be sticking x's into all of these. And then we need to show that it's an excellent approximation. So that means we're doing our f minus g is going to be, so 1 plus x plus, yeah, that's these first few terms. When I put all x's into these by completing the integral, they're all going to cancel. So we're going to get minus t to the 4 over 24, minus x to the 4 over 24. And then we mod it. So that would be x to the 4 over 24. So that's what we're getting for that. And we need this to be less than or equal to, and this was excellent, less than or equal to 1 over 320. Now, I think they said that x was in the range 0 to a half, didn't they? Yes, they did. So x is in the range of 0 to a half. So that means this has got a maximum when x is equal to a half, which means that we're getting 1 over 2 to the 4 times 24. So 16 times 24 is what? 384. So that is equal to 1 over 384, which is less than 1 over 320. So therefore we got an excellent approximation. Right, okay, that was fine. Show that for x is greater than or equal to 0, this thing, h of x minus f of x equals g of x minus f of x. Oh, that's interesting. We've got f of x on both sides. Just cancel those. Plus this integral, which, so we've got h of t and f of t. So there's our f of t. There's our h of t. Right, this should just drop out okay then. So let's just put all these bits in. So if we do, what are we going to do? We want to do, in order to put all of this in, really. So we've got g of x, we've got f of x, we've got, yeah, because these things just cancel. So we need to show that h of x is equal to, right, let's do from h of x then, it is 1 plus the integral from 0 to x of h of t dt. We've also got, though, that 1 is equal to g of x minus the integral from 0 to x of f of t dt. That's coming from here. So that's used this and this. Now we can sub that in for the 1. So we've got h of x is equal to g of x minus, well, actually, let's put that in. It doesn't really matter what way have they got it. Actually, they put it the other way around. So let's do the plus bit, plus the integral 0 to x of h of t dt minus the integral from 0 to x of f of t dt. So we've got that, and that, and then for some reason they've put an f of minus f of x on both sides. So interesting, but we have got what they want. I assume there's going to be a reason. I suppose that allows us to show whether it's a good or an excellent approximation or not, because that's the format that we're looking for, isn't it? So I'm assuming we're going to be using that bit in the last part, or parts, 2 parts left, isn't there, with the question. But anyway, we've shown that bit, so that's okay. Now let's see, you are given that h of x minus f of x, so that left hand side has got a maximum value on the interval 0 to a half at x is x0. Right, explain why the integral on the right hand side is less than that. So, right, okay, so we've got this thing here is, okay, so we've got that thing. We're saying that's got some maximum value. So we've got some function between 0 and a half that's got a maximum value. Then when we integrate that function between a 0 and a half, well, between 0 and something, and we don't know how far we're going, whenever x is between those. So it has to be between these bits from 0 to x, whenever x is in that range. So wondering how this is going to pan out. We've got some function. We don't know what it is. It's got a maximum value. Well, the maximum you can get out of an integral is the width times the maximum height. It's like if you were integrating to get a rectangle, essentially. You know, if we've got some function that's looking like that, whatever it may do, you've got a maximum value. The most you could get out of the integral is a rectangle, but we don't know. There's a maximum value on the interval of that. Okay, just wondering exactly where we're going with this. But let's try this out then. So the maximum we can get, maximum integral is equal to the width times max height. So we've definitely got that. Now in this case, the width is x and the maximum height is at hx minus fx. So we've got x, hx0 minus f of x0. So that's the most we can get. So this integral is, oh, well, I suppose overall, well, this can't go above a half. So the maximum x, max x equals a half. So I don't think it's saying that this has to be less than that whenever x is in that range. Then yeah, okay, right. So the total maximum, so if we're working out the absolute maximum that you could get, then we'll be using a half for x. That will give us the largest thing we could possibly get. So that is our maximum integral. Now for a particular integral, we might not go all the way up to x is a half, but it's still got to be less than or equal to this. So, okay, right, I can see where they've gone with that. So what have I actually written here just to see if this makes sense? Maximum integral is the, right, let's say maximum width times maximum height. That's what we're going to go through here. I didn't put that in first of all. I just went for a width times the maximum height, but we want a maximum width times the maximum height to get a maximum integral. And that maximum width is then a half. So we can just ditch that x and put a half in there instead. And then that is the most we can possibly get out of that integral. So it must be then the left-hand side is less than or equal to that. Okay, well, that seems fine. Right, I've filled up the sheet now. Have I got another one? I hope so. And yes, I do. Last part then, you are also given that f of x is less than or equal to h of x for all x is 0 to a half. Show that f is a good approximation to h. Right, okay. So now we have done, it feels like they have walked us towards this in the last two parts, because we've done a lot of work on all of this. So we say, because this integral here that we've got is that. So they've been working us towards this, as they always do in these questions. So we've got that stuff here. So we've got to show all of this. Right, well, let's just put in then x0 on that. Is that what we want? You're also given that f of x is less than or equal to hx for all of that. Show that f is a good approximation when it's in that range. Well, let's try for x0, because at least for x0, we're going to be getting lots of these things appearing in it. So yeah, I'm going to, because this is the thing, you see, if we replace this integral here with this, then we're getting x0s. So really it'd be nice to have x0s in these, and then we've got x0s everywhere. So let's go with that. So hx0 minus f of x0 is equal to g of x0 minus f of x0. And then we've got this thing, which has got to be, well, it's not going to be equal anymore because this is less than or equal to that. So we're going to be turning this from an equals into a less than or equals there, and then adding on a half h of x0 minus f of x0. Okay, so it'd be nice to take this off both sides, wouldn't it? Because then we're just going to have half on this side. So if I do that and then double everything, and then we'll be back to having the same left-hand side. So I'll do that, h x0 minus f of x0. So I've taken that half of it off, then doubled everything up. So we'll have to have 2 gx0 minus 2f of x0 on that side. Right, question is, so what? I think is the response to that. So what indeed? What have we done on this? Have I missed something? Because this is what we want. We want this in order to show that that is a good approximation. So we need something to do with this. Is this something that I've already done and I've forgotten about? What else have we done with G's and F's? G's and F's, here we go. G's and F's. We did this in whatever part that was, part 3. Part 3, we showed that the difference is 1 over 384. That's the magnitude of the difference, 1 over 384. So we got 2 lots of that difference. So that's going to be less than or equal to 2 over 384. And that is then, well, that's going to be less than, that's less than 1 over 100. What do we want, a good or excellent? Yeah, it's going to have to be good, isn't it? Yeah, good approximation, yeah, because it's not going to go with the excellent one, because the excellent one was 320, wouldn't it? So, yes, so we've shown that that's what we want. That's what we've got, I mean, that the difference between those is 200 is less than or equal to 2 over 384, or 1 over 192, which is less than that. Okay, that was a strange question. It was a nice question, though. I mean, that's yeah, some good numerical methods there for finding these approximations. So I do like it. It's very informative of how you can put these things together in order to construct approximations, at least in a limited range of 0 to 1/2 for the x values. But yeah, mainly it was following it through. Again, they add the usual build up here. Each step was leading to the next. So we needed 3, 4, and 5 in order to do 6. So yeah, I mean, I suppose actually we could have, even if we hadn't done part 3 and got that 1 over 384 answer, by seeing that it's an excellent approximation, then we would know that it was less than or equal to 1 over 320. So when we got 2 of them, we're still less than or equal to 1 over 160. So you could still do the last part of the question, even if you hadn't got the actual answer to part 3, because we've got that excellent approximation already worked out. So yeah, you could still step through in order to get that coming out nicely in the last part of the question. So yeah, that was a very interesting one.